Synchronous generators. So any generator, either synchronous or asynchronous, is used to produce electrical power, or you can say generators convert mechanical power into electrical power. And synchronous generators produce AC electrical power. When we're looking at that, there is a magnetic field either produced from a permanent magnet or from electromagnet, and then we look at its interaction with its surroundings. So let's assume a case that we have a magnetic field produced from an electromagnet, which is a stationary magnetic field, now static, and now you place a rotating loop of a conductor or a conducting wire, you can say. Once you place a rotating loop inside the stationary magnetic field, there's going to be EMF, or the AC voltage induced around the or at the two ends of the conductor or the coil, and that induced voltage or EMF is given by E induced equals to phi, then the speed of the rotating coil, and sine of omega t. So you will see that this is the voltage induced, AC voltage induced across the two ends of the coil. That's the magnetic field produced from a permanent magnet or from an electromagnet. That's the speed at which the loop is rotating, and this shows the shape of the induced voltage with respect to time. So this will be the shape, the AC we're expecting for this electrical power. It's the same principle used behind the generators. The only difference is in case of a synchronous generator, the magnetic field is not stationary, it is rotating. So magnetic field is of rotating type. How this is produced? You use a field winding of the synchronous alternator, and then this field winding is fed from a DC, which is constant source of power. And once there is a current flow through the field winding, there will be a magnetic field, but that will not be rotating. Then you will use a prime mover to rotate the part on which this winding is bound, and that will produce a rotating magnetic field. Now that's one part. Now this rotating magnetic field is going to be linked to the coil which we have talked about, or the loop which we have talked about earlier. Now let's say that loop is placed inside this rotating magnetic field. Now that loop, or we call it a loop with many turns, and we call it a coil with, let's say, n c number of turns. And this loop does not need to be rotating anymore because we have produced the rotating magnetic field. So this is a stationary loop now. And this winding, or a loop, coil as well, stationary coil, is on the armature of a synchronous generator. So that's why we call it armature winding or armature coil. And this armature winding is of a three-phase type. So we talked about the two types of connections for the three-phase systems, the Y connection and the delta connection. Please refer to the notes in order to make sure that you review this before we do this. Okay, so armature winding is the three-phase. Okay, so the rotating magnetic field produced from the field winding is able to induce that voltage I induced in the three phases of this armature winding. And now that induced voltage is changed to N, which is the number of turns, phi and omega N, and sine omega N mt remains the same. Let's define this whole portion equals to EA and sine omega t. Here this EA will be called internally generated voltage. Internally generated voltage inside the machine. So in the three-phase armature winding, let's say in one phase the voltage induced is given by EA to A prime. So that's what we're saying for phase A as a function of T, of course. And C phi omega, which is EA, we defined sine of omega T. In the second phase, we're aware that the voltage will have the same amplitude. So EA or this NC phi omega will remain the same. Only difference will be in the phase. So there will be a phase shift of 120 degree. Let's say for phase we're saying it's negative 120. So this is giving us the positive phase sequence for the voltage. And the third phase is the phase C, for which again the amplitude remains the same as in here, and the phase will be omega t minus 240, or it's the same thing, you write omega t plus 120 as well, one and the same thing. So what we realized that we supplied the DC current to the field winding of a synchronous alternator that has produced the magnetic field. Now the component on which field winding is bound is called the rotor, and this is rotated with the use of an external prime mover. So it results into rotating magnetic field. And then you place the armature windings inside that rotating magnetic field. It induces the three-phase voltage in the stator or the armature windings. Since the armature windings are the stationary part, that's why they're also called stator windings. Now the speed of the generator. Speed of the generator, which is this part, if you see, depends on the speed of the rotating magnetic field. So speed of the generator is same as the speed of the rotating magnetic field, and that speed is in RPM. Now here I used omega m, which is radians per second. Here this is RPM, rotations per minute, is given by 120 the supply frequency divided by the number of poles. So this is the electrical frequency. It's the frequency of the voltage which is induced or produced from the generator from its stator or armature winding. So that's the electrical frequency, electrical power frequency, and the units are hertz. And here this is the number of poles the machine is bound with in order to produce the magnetic field which is rotating on this speed. So N is again the Nm is the speed of the generator, or you can say this is the mechanical speed of the generator. Mechanical speed of the generator in RPM, rotations per minute. So in order to generate 60 hertz electrical power, you need a two-pole generator to be running at 3600 RPM. That's just one example. Let's say you have a four-pole generator that to produce the same 60 hertz of frequency, to produce the 60 hertz electrical power, it will be running at 1800 RPM. Now let's look through an example. Okay, let's look through this example. A two-pole generator has a stator diameter of 0.5 meters and 3 windings with 15 turns, each having a length of 0.3 meters into the page, assuming a rotor producing a field of 0.2 Tesla and a rotational rate of 3600 RPM. Find the induced voltages in the three stator windings. Also calculate the RMS phase voltage and the terminal voltage of the generator for Y connection. All right, so we're looking at first the induced voltages in the three phases, as one of the equations for phase A is in here. So let's continue with that. Okay, so EAA prime and C phi omega m sine omega t. So in that case, the induced voltage in phase A of the stator winding will be NC, which is the number of turns, which is 15 in our case. We also have to look for what we're gonna do with the phi. So we have to go back into the details of phi. So phi is given by area times the flux density, and for a loop of length L and other dimension the width half as the radius r, so let's take 2r as the width times the L to find the area B. So in that case, let's figure out the phi first, which is 2 multiplied by the radius, which is 0.5 divided by 2. So that's the diameter, radius is half, multiplied by the length, length is 0.3, and the flux density, magnetic field density here is 0.2. So with that you will be able to have phi in Webers because all the dimensions are in their standard units, so that's phi. Okay, so let's see what is the EAA prime then. So we have MC is the number of turns, which is 15. Flux we calculated here is 0.03, and the speed, now speed has to be in radians per second, and we know the conversion, it's 3600 in RPM divided by 9.55. Now 9.55 again is a constant calculated as 60 over 2 pi because we're converting RPM into radians per second. So sine of omega, I'll come to this omega soon, and t. So this omega here is the same thing as we have calculated. So 3600 RPM goes to 377 in radians per second. So you can substitute that omega as 377 in here. So you can simplify whatever this comes to. So let's say it comes to, so let's say it comes to 169.7. I hope that you will be able to complete your calculation. So EAA prime comes to 169.7 sine 377 T in volts again. Okay, that's for phase A. Now for phase B, we do not need to calculate the amplitude. It's gonna remain same 169.7 sine 377 T, and I'm gonna say minus 120, and again in volts. And for the phase C, it's 169.7 sine 377 T. Either it's minus 240 or plus 121 and the same thing. So you can look at this as a 4-quadrant space. Okay, so this is giving you the amplitude. When we look at AC, so any instantaneous value of AC is given by root 2 times V, and this is the RMS value. So based on that, we have root 2 and the RMS value is 169. So let's say we're looking at the RMS value of the phase voltage. Then what we're going to do is we're going to say it's 169.7 divided by root 2. And the calculation give you 120 volts. So for all the 3 phases, it's the same. The voltage is 120 volts as the phase voltage. The terminal voltage now, when we're saying terminal voltage, so it's asking for the terminal voltage at the generator for a Y connection. So in case of Y connection, the line and the phase voltages are different. In case of Y connection, so the terminal voltage, which is the line-to-line voltage, is given by root 3 times the phase voltage. So root 3 times 120 gives you 208. This is phase and line quantities, has nothing to do with the RMS or non-RMS. This is again the RMS value of the AC voltage, but this is the line voltage. So once we calculated phase, the terminal voltage of the generator is always the line voltage. So line voltage in case of Y connection is √3. Let's say if it was a delta connection, in that case the voltage line to line remains equals to the phase voltage. In order to have more information about it, please check the three-phase systems unit.